Hello everyone, how are you? I hope you are doing great. I am Pulak Maiti, your chemistry teacher. Today we are going to discuss haloform test or haloform reaction. It is also known as oxidative cleavage of methyl ketone. Let's start with a question. Suppose I give you this compound, CH3, CH double bond, CH, C double bond O, CH3. This is what? A alpha beta unsaturated ketone, right? And you want to convert it into CH3, CH double bond, CH, C double bond, OH. So what you are doing? You are oxidizing a ketone part, right? The ketone unit into carboxylic acid. If you notice that this compound, this product contains one carbon less, right? This carbon is missing here. See, oxidation of ketone is always difficult. Why? Because it involves carbon-carbon bond breaking, bond cleavage. In organic synthesis, in any kind of organic synthesis, if you have a reaction where there is a carbon-carbon bond cleavage, this reaction is difficult. That is why oxidation of ketone is also difficult. How you oxidize a ketone? You oxidize a ketone by using a strong oxidizing agent. Like if you want to oxidize CH3, C double bond or CH3, so on oxidation you will get CH3CO OH plus HCO2H. So you have to break this carbon-carbon bond. This is not easy. You can only do this if you are using KMnO4 in alkali medium and that too heating. So this difficult or drastic condition is required for oxidation of ketone. But here you cannot use this condition. Why? Because you know there is a carbon-carbon double bond also. Under such condition, carbon-carbon double bond undergo oxidation. First you make diol, then it will undergo again oxidative cleavage. So here what you are doing? What? The question is oxidize this ketone but without hampering this double bond. That is difficult, again difficult, right? And in that case, in such cases, haloform reaction will be very useful, right? So what is haloform reaction and what is the mechanism of this haloform reaction? How it is useful for synthetic application? That is our today's topic of discussion. So let's begin. So if you have a ketone or aldehyde which contain this ketomethyl group, this is called ketomethyl or methyl ketone. If it is connected to a hydrogen or let's say any alkyl group or let's say any aryl group, right, like phenyl group, then in presence of excess halogen, like let's say I will take iodine, okay, and strong alkyne, both should be in excess, right? What will happen? This methyl part, that's why ketomethyl, this methyl part will be converted into CHI3. If you are taking another halogen like chlorine or bromine, you will get CH3 or CHBr3. Remaining part, the remaining part will be a salt of carboxylic acid. See, you have hydrogen CO, so you will get HC double bond ONA. You have RCO, you will get same product RC double bond ONA. You have PHCOONA, right? That is what is haloform reaction. So that means it is a oxidative cleavage of methyl ketone. These are let's say methyl ketone. There is oxidation as well as cleavage of carbon-carbon bond as well as oxidation. This part is going to convert it into carboxylic acid, sodium salt of carboxylic acid or potassium salt of carboxylic acid. This part is going to convert it into what? Haloform. In case of iodine, we will call it as iodoform test. Why iodoform test? Because you know this compound is yellow colored solid. Yellow solid. So application number 1. If you want to know that you have an unknown compound, if it contains ketomethyl group, to identify ketomethyl group in an unknown compound, you use haloform reaction. This is a note that you must note it down. Okay. To identify ketomethyl group in an unknown compound, haloform reaction can be performed. Clear? So this is what is your haloform reaction. First, I will tell you what is mechanism, then I will discuss what is the usefulness of this such reaction. Okay. So you know that if you have a carbonyl compound, so answer to this question. This is nothing but haloform reaction. Haloform reaction is specific for this methyl ketone, no? So it will not hamper this one. That is how useful this reaction is. Okay. Okay. Now, if I want to discuss the mechanism, okay, what will be the mechanism? See, why we need this keto-methyl group? See, in keto-methyl group, this is ketone, electron withdrawing, and this is alpha. Alpha proton to a ketone are acidic, right? Alpha proton to a ketone are acidic, that we have studied in GOC chapter. We know that it will undergo keto-enol tautomerism because this proton is acidic. Undergo keto-enol tautomerism, and what you will get? You will get this enol form. This is keto form. I can say this is keto form, and this is enol form. But because it is a alkali medium, what we can write in alkaline medium, you can write it as CH2 double bond O minus. So this ketone, this is called enolate. Anion of enolate. This enolate formation is crucial. If you have this enolate, then your haloform reaction will take place. So this is your step 1. Consider as step 1. What is step 2? Step 2 is the reaction of this enolate with a halogen, right? So what will happen? Let me write in this way: O minus double bond CH2. Now you see, you have halogen. Here you use iodine or bromine or chlorine. What will happen? This bond will move this way. Now this pi bond will attack here. This bond will break. Okay, what you will get? You get RC double bond O CH2 X plus what? X minus. So now what you have? You have alpha halocarbonyl. That is your step 1 and step 2. And once you have a alpha halocarbonyl, same step will be repeated again and again until all the hydrogen are replaced by halogen. So what is your next step? In the next step, this will be your starting material. Okay. Step 3 basically repetition of step 1 and step 2. So RC double bond O CH2X. Again, I write step 1 and step 2 same enolization, then attack to halogenation, halogenation. What you get? You will get a dihalo compound CHXX, right? Again step 1 and step 2. Okay, step 1 and step 2. Okay, then you will get RC double bond O CXX, trihalocarbonyl you will get. It's very interesting chemistry going on here. See, this enolization is catalyzed by base, right? And that is why enolate will be formed. Enolate will attack this halogen and you will get monohalocarbonate. Now what is the next step? Again formation of enolate. But you know, for formation of enol or enolate, this proton must be acidic, right? Initially this proton has an acidic character, but once you bring a halogen which is a electron withdrawing group, the acidic character of this hydrogen increases. That is chemistry that we have learned in GOC chapter, right? Because this proton is more acidic compared to this step will be faster compared to what was the rate of the reaction initially. Because you have a electron withdrawing group at the alpha carbon, rate of enolate formation will be faster for the second halogenation step. Same rate will be more faster in the third halogenation step. It is like once reaction is started, okay, it's like initially if you have motivation for study, okay, once you are motivated, you are more motivated for the next level. It's like that. So once one halogen is coming, next halogen will come faster, third halogen will come more faster, and ultimately you will get a trihalide halocarbon. Once you have the trihalocarbon compound, next is your carbon-carbon bond cleavage. So what is your next step? Next step is this cleavage of carbon-carbon bond. Okay, please note it down. It's very important. RC double bond to CH3. Okay, why this carbon-carbon bond will cleave easily? Because it cannot cleave in the middle step. Okay, it cannot cleave in the middle. Only in this case it will cleave because this now is a very good leaving group. Okay, if you have OH minus in your condition you have already, this will break. What you will get? RC double bond OH plus CH3 minus. This will exchange proton, so you will get salt of carboxylic acid plus CHX3. Now if I ask you why this CH3 minus is better leaving group, you can easily answer. We have studied this in chemical bonding and in JOC. See, this is halogen like iodine, fluorine, iodine, bromine and chlorine, not fluorine. Iodine, chlorine and bromine, they have vacant d orbital, so there will be a back bonding. That is why they are very stable, and once these are weak base are better leaving group that we have studied. That is why this reaction is again favorable. And that is the mechanism of haloform reaction. I hope it is clear. If you have question, you can ask. Okay. So now we know what is haloform reaction and what is the mechanism of haloform reaction. So before going to the synthetic application, okay, let me also tell you, haloform reaction is not only for carbonyl compound with keto-methyl group. It is also applicable for alcohol. Now let me tell you. You know what happened? When we are treating iodine or chlorine or bromine with alkali medium, generally we take dilute and cold alkali medium. In this condition, they form what? They form NaI plus NaOI plus H2. This is true for chlorine or bromine also. So if you are this NaOI, this is called sodium hypoiodate, okay, or sodium hypochlorate or sodium hypochromate. These are oxidizing agent. These are oxidizing agent. Okay. So if you have a alcohol, which contain CH3CHOH unit, right? If you have this unit, CH3CHOH unit, like for example, ethanol. This is nothing but ethanol, which contains CH3CHOH unit. If you have this and if you treat this with I2NaOH, what will happen? This will form NaOI, which is the oxidizing agent that will oxidize this part, CH3CHOH unit. So it will oxidize and it will get what? Get this ketone. So not only for carbonyl compound, also for alcohol which contain a group which can be oxidized to keto-methyl. Alcohol, if it has CH3CHOH unit, after oxidation it will be CH3C double bond. That means a group which after oxidation is converted into keto-methyl group. That also give you positive haloform test or iodoform test. Now you know, since acetaldehyde gives you positive iodoform test, right? Positive iodoform test, CHI3 plus HCO2Na, right? That means ethanol also will give you positive iodoform test. So not only for aldehyde or ketone, but also for alcohol, and for alcohol you will get iodoform test. So if I give you a general question like which of the following compound, which of the following compounds will give positive iodoform test. Iodoform test. Why we are calling it as iodoform test? You know what? When you are making iodoform is what? Iodoform is a yellow solid compound. That means you are getting something which is indicating that your reaction is done. So colored solid compound formation means your reaction is done, and that is why it is called iodoform test. Okay, you cannot get a colored compound in if you are making chloroform or bromoform because they are colorless liquid. That's why iodoform test. Okay, basically same reaction, right? So suppose compounds are there like CH3OH, CH3CH2OH, CH3CH2CH2OH, CH3CHOH, CH3. Okay, this is what methanol, this is ethanol, propanol, isopropanol, let's say butanol, CH3, CH2, CH2, CH2OH, and CH3, CHOH, CH2, CH3, CH3OH, CH3, CH3. These are some alcohol. Which alcohol will give positive iodoform test? See, it does not contain this this group which can after oxidation will give keto-methyl group. That means it does not contain CH3CHOH unit. Because it does not contain this unit, it will not give positive iodoform test, right? But this contains, so it will give you positive iodoform test. Is this content this group? No. So it will not give positive iodoform test. This will give you positive iodoform test. This will not give you positive iodoform test. This will give you positive iodoform test. This will again not give you positive iodoform test. So suppose there is a question ki how to distinguish between methanol and ethanol. Very common question. How to distinguish between methanol and ethanol, right? Haloform test, one of the answer. Right? How to distinguish between two positional isomer of butanol. One butanol, two butanol. How to distinguish between two positional isomer? By iodoform test. Right? Similarly, if you have a carbonyl compound, suppose I will give you, this is clear, right? Suppose I will give you this carbonyl compound. We have reactions like tolerance test, Fehling test to distinguish between aldehyde and ketone. I am giving you two aldehyde, HCHO, CH3CHO. Can you distinguish between can you distinguish this by using tolerance test? No, because both will give positive tolerance test. Then, but you can use iodoform test to distinguish, because this will give negative iodoform test, this will give positive iodoform test. So now you understand to distinguish between some alcohols, some position isomer of alcohols, or aldehyde, two different aldehyde, formaldehyde, acetaldehyde, or some position isomer of ketone. I am giving one more example. Suppose you have two pentanone and three pentanone, CH3, CH2, C double bond O, CH2, CH3. See, these are two positional isomer of pentanone. You can distinguish by them, because you cannot distinguish using tolerance test again, right? Because none of them will be positive tolerance test. But if you use iodoform test, this will give you positive iodoform test, this will give you negative iodoform test. Now you understand that this haloform reaction is very useful in distinguishing between isomers, right? Alcohols, ketones, aldehydes, very useful. Huh? Okay, now you must remember that there are compounds which contain keto-methyl group but does not give positive iodoform test or positive haloform test. Like for example, if you have CH3, C double bond O, and it is connected to a OH group, right? CH3, C double bond O, it is connected to a OR group, right? CH3, C double bond O, it is connected to a O, C double bond O, R or CH3. CH3, C double bond O, a halogen, or CH3, C double bond O, a nitrogen. All these contain a keto-methyl group, but none of them will give you positive haloform test. Why? This is important. See, in a haloform reaction, what is the most crucial step? The first step, formation of enolate, right? If enolate is formed, remaining reaction will be faster. Halogen will be faster. Then second halogen will be faster. Third halogen will be faster. But what happens is, whenever there is a heteroatom connected, no, there is a heteroatom connected to this, what happens is there is a resonance or conjugation with this carboxyl double bond, which will decrease the positive charge density of this carbon. And that as a result, because there is a decrease in positive charge density, means this carbon is not enough electropositive. Enolate formation will be less. Because enolate formation will be less, your reaction will be prohibited. Means haloformation will not take place. So simply you must remember that if the condition I am saying ki it should have keto-methyl group, but let's modify it. It must be connected to either hydrogen or alkyl or aryl group. If it is connected to another group like this, right? Will it be Haloform test? No. But that is a very interesting question. Okay. Like if I ask you, suppose if you have CH3, C double bond O, chlorine, and CH2 chlorine, very simple one, there is no difficulty here. Let's say there is hydrogen. Okay. Now out of these two, which one will give you positive haloform test? See, this contain keto-methyl group, CH3CO unit, but it will not give you positive haloform test. Why? Just I mentioned, because it is connected to a heteroatom, right? So it will not give positive haloform test or haloform test. But does it but it is connected to hydrogen now. But does it contain keto-methyl group? It's not exactly keto-methyl group, but still it will give you positive haloform test. Why? Because you see, if you start with this one, CH3 C double bond of H, after enolization and monohalogation step, this will be your intermediate now. So if you are starting with intermediate, of course it will give you positive haloform test. Like if you are treating CCl3 C double bond OH with OH minus, right? Obviously you will get CHCl3 plus HCO2 or HCO2 minus, right? That means if you are starting with the intermediate, obviously you will get positive haloform test, right? So this is one point that you must remember. Sometimes it's simple tricky question here. Okay, this is what you should remember about haloform test. So we will solve a question. Okay, now we don't have much time, but you can take at least one question. Like convert. Suppose there is a question. Convert this one, or identify the product. Sorry, you can write identify the product of this reaction. So you are treating this with KBRO, right, followed by H plus, third is heat. What will be your product? You have to understand this KBRO. This is what is this KBRO? This is the condition for haloform reaction. Here the halogen is bromine, like I mentioned na, NaOX. This is your hypohalide. This is the oxidizing agent. Okay, as well as it can perform haloform test. So what will happen? Because you see, this is your keto-methyl group. This is not keto-methyl. This is your keto-methyl, right? Why? Because it is directly connected to C double bond, na? It is alpha carbon receptor. It is connected to alpha carbon, right? So this carbon will be accordingly into what? CHBr3. So what will be your first product? Your first product will be this CH3 will remain as such, but this CH3 will be converted into CHBr3. Make sense? That is when you treat this with KBrO. Then in the next step you are treating this with H plus. That means you convert it into carboxylic acid. CO2H CH3. Now please remember, if this you will learn in carbonyl chemistry, in carboxylic acid chemistry. Whenever there is a beta keto carboxylic acid, on heating it undergo decarboxylation reaction. This CO2 part will be gone. So what will be your product? Your product will be C double bond of CH3. You will get a plenty of question in your modules, in your exercise on the application of haloform reaction, right? One point, additional point you must remember, that if you have what is this? 1,3-diketo. 1,3-diketo compound, diketo carbonyl. Although it does not contain keto-methyl group, but if you treat this with, let's say, iodine NaOH, it will give you iodoform test. And what will be your product? See, this carbon, okay, will be converted into CHI3. So the remaining compound will be ONA. I want all of you to try the mechanism of this reaction. Please try at home. So this is your home task. Okay. So there is a point. There is a compound where there is no keto-methyl group, but still you are getting what? You are getting iodoform product. So that's a very special case that you must remember. And please everyone try the mechanism of this reaction. Okay. This is your homework. So before I end, let me summarize. So today what we have learned? We have learned what is haloform reaction. Haloform reaction is nothing but oxidative cleavage of keto-methyl group, or methyl keto. As I started, this haloform reaction is specific oxidation reaction for keto-methyl group, where methyl group will be converted into haloform, the remaining part will be converted into carboxylic acid. This condition does not affect groups like other oxidizable group like carbon-carbon double bond, right? So if you have a compound like carbonyl compound which contain keto-methyl CH3CO unit, it will give you positive haloform test or positive iodoform test. And alcohols which contain some groups which after oxidation become keto-methyl like CH3CHOH unit, that also gives you iodoform test or haloform test. So this reaction is useful or helpful in distinguishing between formaldehyde, acetaldehyde, methanol, ethanol, L-propanol, isopropanol, okay, 2-propanone, 2-pentanone, 3-pentanone. So to distinguish between such compound, this test can be used. It's a very commonly asked question. Then this synthetic application, convert this to this kind of reaction are also very important, right? But it is not applicable for compound where keto-methyl group is converted to a heteroatom. So it is not possible by carboxylic acid, like acetic acid will not show, or acid halide or amide or ester or anhydride will not show this haloform test. Okay, so you have noted your homework. Okay, make sure you submit this homework to in your next class, and if you have any doubt you can ask now. Okay, thank you for your patience.